Yeah, let's begin a little early. Okay. My name is Vadim. I work in TerraCloud Denmark. I work in a compilers team for a few years, maybe 5. Yep. And today we believe that our compilers are in pretty good shape. They're stable. We build compilers with our compilers optimized, and then try to build them a little more, like 3 times, 2 times. Like just like chain of building. It's like vodka. Yeah, yeah. And we built some layer products with optimization natively on x86. And for a while we playing with the OS itself built natively with optimization on x86. So maybe it's not quite a right name of the presentation. It's not the bugs that came when you ported something. It's bugs that are exposed while porting because the architecture is different and some things are different on the x86 than on Itanium. For example, Itanium has more than 100 registers, and on x86 it's like 30. Yeah. So porting your application to x86 is easy for well-written programs because all the interfaces are the same. So we're trying to support all that was supported on Itanium. So it should be just build, link, and run. But sometimes in the old code, there are some bugs that have been there for 30 years. And it worked magically by mistake. You were under the right star. I don't know. Yeah. So these presentations will show some debugger output, DCL output, listing files, and assembly. And I'll try to explain some lines. So there is no agenda. There's just a number of problems. To be like, I don't know, curious, to not know in the beginning what the problem is. It may be more interesting. So this was fine by me. I was playing on the natively built OS, and I tried to clone some repo, some Git repository, and this was the fail. It works fine on the cross-built operating system, so it should be normal on the native one. And we can see here it says access violation, so we touch some memory that not belongs to us. And as we see virtual address, so it means that we access the pointer that equals 698. Oh. Yeah. So there is a program counter that we can check by analyze system. Let's do that. We run analyze system, do the map and our address, and we see that the failure occurred in module libmalloc and a certain offset. We keep all the disassembly of our system models just in case. That's for this kind of cases. But sometimes it shows only offset and not the module name. In that case, you need to manually calculate using the map files, listing files, what the problem instruction is. Yeah. Yeah. So this one is easy. A little easier. So we look at that offset. We look at the disassembly, and we see that this one is problem is 12AB that accesses some data. And we see 698 that was in the virtual address. So it means that RBX was 0. But program awaited something there. So the operation load effective address is used much by LLVM optimizer to do the 2 operations at the same time, just to zoom and then save to another place. So what's happening here? We just sum RBX with 698, put it to R8, and then access it. So in R8 is the 698 number stored, and then we got access violation. we can check in this assembly how RBX used in our whole function. Because the LLVM optimizer can mix the registers using like different ways. In our non-optimized cross compilers, all the local variables are stored in the memory, not in the registers. And when we turn on optimization, LLVM starts to mix all the things into registers, Some things, of course, will be stayed in memory because there is not so much place in registers. So we can check, and I did it off cartons. So I found only one usage, whereas some address of the variable was stored in the RBX. And right after that, there was checked that it's not 0. And as we saw before, yeah, it was 0. And after checking for 0, it was jumped somewhere after our problematic place. And of course, if the program is highly optimized, it can jump back and forth, but not in that case. So yeah. So logically, RBX could not be 0 in our problem place. So maybe it was poisoned by some calls. Let's search for calls. Luckily, there are only 2 of them. One is the system one of the field that is like memset on OpenVMS. And then it was called to VM, the internal VM malloc. So it looks like this one is bad. And I need to mention that any attempts to add tracing or something or logging avoided problem because LLVM mixed using the registers. Sometimes you cannot add just, I don't know, print to show the problem. So what changed? Because LLVM mixed all the things. It decides to use different registers to store different data there. And if you look at this assembly of VM malloc, we see that RBX is actually stored on the stack in the function prolog, and at the epilogue, it was restored from the stack. So it was poisoned somehow in the stack, being saved. Right after pushing RBX, it's the local variables allocated. So we just move the stack, and there lies all the local variables. So it looks like it was poisoned along with one of these variables. And you don't know which one because, again, LLVM mixed them how it wanted. Now there is 2 ways. You can search through this assembly of the VM malloc, but it's large and highly optimized. Or you can use a debugger. But failure occurs after a couple minutes of Git work in the nearly random percentage, like 72%, 74%, just somewhere. Yeah, we know that second one is more fun to use the debugger, not the sitting and looking like weak and the disassembly. But luckily, we had near 15,000 internal compiler tests, and there were a few with the same failure. There was the code that does nothing in the test itself. It's like many figure brackets inside each other, and just nothing. But luckily, it's the same failure. We see that it's still virtual address is the same, and the PC is the same. Trust me. Yeah. And here we can use the debug. But you cannot set a breakpoint to the system shared library, like where the VM malloc is located. I don't know why. You just can. So you need a trick. You need to define librtl to the same image, just add semicolon at the end. I'm not sure how it works.
But semicolon prevents the image activator from doing a known file lookup.
Yeah, thank you.
So it doesn't look for installed file.
It's installed. Yeah, okay. So then we rerun the compiler, and we see that the PC now in the user space. So here we can set the breakpoint. We can look inside. And we can run the compiler in debug mode. So I hit all the qualifiers that need to be written to run the compiler in debug mode. Yeah. So we set breakpoint to exception, run the compiler, go to screen mode, and we see the disassembly that is in the problem place, as we saw before. It's like the 698 put into RX, and then here payload accurate. In your machine, the debugger output may look different because you can configure some to not see in the Q letters, but something different.
Translator.
Yeah. Again, I don't know how to do that. I just I just don't care. Yeah. And using the instruction here, the offset of instruction and the listing file, we can find where was the libmalloc, where is the vmalloc call that is suspicious to us, and we can set a breakpoint to that address. I calculated it by myself. Because in debugger you can see the function names, only offsets, only relative offsets. So it's this call is the one that suspicious. And vmalloc is a very basic function. It's just a malloc. It will be called dozens of times. How can we find the bad one? Because we don't know. We can set a breakpoint, go inside, and it will work fine. Or sometimes. So we can use the debugger for that. We'll create the input file and put the commands that debugger will execute and pass it to the debugger. So on our call, we set the trace. Every time when debugger will go to that call, it will print a message trace at this offset and some other information. Then we do set break exception to stop execution on exception, then run and then exit to not print in more traces after the exception. So we will find the bad call. We do define sys input to our file, define sys output for the new file to see the output of the debugger, and then run the debugger. And in out.txt, there will be whole debugger output. And we can just calculate how many words trace at, how many lines with trace at are there, to know how many calls were fine and which one is bad. And we can just use search with the qualifier statistic and output NL. Statistic will show some information, how many lines were scanned, how many lines were found with trace at. But output NL prevent to print all these lines because they are basically the same. So any guess how many times malloc called during
1,000.
10,000? Yeah, it was pretty good. It's just 5,617 times. This means that 5,617 call was bad. And in the debugger, we can set a break and skip certain amount of the encounters. So I checked a couple times. The number was the same every time. Yeah, it was stable. So it was 100% reproducible. Luckily, maybe, I know. Yeah. So we do set break, then step into to go into our bad call. And we set screen mode and display instructions to see the assembly output. Now we're inside of the vmalloc. It's the same, the push in RBX, and then local variables allocate. So each push decreases the stack pointer. So we can calculate at which point of stack, at which address RBX is actually saved before it was poisoned. We just using the step instruction, go to line after pushing RBX, and then examine its content. So it's in decimal mode, but I don't know, for me it's fine. So this is the actual address where the saved RBX is. And we can set watch to that memory. We do set watch. We're still inside of the function after the pushing. We do set watch and run the program to completion. And we see that the data was overwritten. So there was alt value, some value, and it became just 0. So memory allocation was overwritten. That was supposed to be saved until the function execution and to be popped to the RBX. And we see where it occurred. It's some call. And looking at all the instructions before and after, we can find the place in disassembly, because again, we can see the function name here. So we go to disassembly and we see that this is the call of sysexpreg64. Going to the system services reference manual, we see that there are some 64 bits parameters. There are like pointers to 64-bit variable, and some also pointers. So we need to find that code in the source code or in the listing. It's a very old code. It has many if-defs checking for architecture, so it's hard to find by eyes where the problem is. So there is some macro that called another macro and another macro in a couple times, actually many times. And we can see that there is some parameter, that new heap size. When you call expreg, it returns you new size in that variable. And we see that this variable was actually 32 bits. But the manual said that it should be in 64, so it should be 8 bytes, 64 bits. So when the sysexpreg wrote something inside, it also garbaged our saved RBX. So the fix will be easy, just make variable 64 bits. This code was there for, I don't know, 30 years. It just worked. So we think that it's because of the back to alpha. Alpha wanted all the variables to be aligned to 64 bits. So our old front end called, or our old backend called gem, it aligned all the variables by 64 bits. So it did garbage some memory, but it was not used memory at all. So the fix is pretty easy. I think I spent maybe 3-4 days to find it, because I used the wrong approaches. Yeah, maybe. Because it's the experience. So yeah. So now there are problems with variables being too small. It's the first kind of problems that we see in the live products in the OS code. Another example is allocating array that is too small and accessing it out of bounds. Because of 64-bit alignment on Itanium and Alpha, it worked fine. Because Itanium is actually created array with 16 elements, not 10. So, any questions for now? Yeah.
Have you ever run across a problem that worked on one system, but not in a different system?
If it was, there was some incorrect programs that were just.
Yes. There was an incorrect problem.
Yeah.
But some systems it would run on, some systems it would not run.
Yeah. Yeah. When I tried to reproduce it manually by hand to write some program, it didn't reproduce, because the stars and maybe
right. Because we don't know. We got lots of different x86 type chips.
Yeah.
So work differently, right?
Yeah. Yeah. Sure. Maybe on.
So lucky.
Yeah. Maybe on some systems, saving register will be in different order. Like
that's it.
Maybe there is some saving space after all the registers.
I think it's the out of order execution.
Yeah. Yeah, so we haven't seen anything on anything that. But these kind of problems are, I don't know, maybe 10 times I've seen. First time was the hard to find, but the other times it's more easier and easier and easier to find because you get an experience. Okay, so then this problem found during OS installation. While updating memory disk, there was again access violation. Virtual addresses, there is something number inside, and the PC is strange. I don't know what does it mean. It looks like the descriptor because one part of the like address, yeah. But this program is small, and the problem was easier to find. And here I could use just printfs to see what happens, what is wrong. So what we see here, there are two descriptors allocated. One is already filled, and another one is filled during the CLI get value. And at the end of the buffer is set 0 to string be 0 terminated for some reason. And when we go to the manual about CLI get value, we see that return length is supposed to be word, so only 2 bytes. And when we go inside of the source code of this CLI get value function, it's on Bliss. We see that only 2 bytes is filled, and the other bytes are kept untouched. So if there was anything, it will be there still. And going back to the source code, we see that our variable is 4 bytes. So there is just some garbage from the stack. And to fix that, we can either zero initialize it or make it short, just 2 bytes. I'm not sure why does this work on Itanium. Maybe there is some protection by the hardware. I don't know. So that zero initialized all the stack or something. Because in the code, in the disassembly of the Itanium code, I can see any manual zero initialization of the variable. So again, lucky star for 30 years, maybe 20. Anyway. Yeah, so this is the opposite problem where variable is too big. First one was variable too small. This one is too big. Any questions? Another problem is, again, on natively built OS, show license just prints and prints and prints all the licenses, all the list of licenses endlessly. I put here the critical part of the code on Bliss. So it has the local variable, and it asks if there are some qualifiers there, and fills the local variable, and then stops when the variable is not equal to comma. So we check if there is a comma, like when you do show license and you present the products divided by comma, like show license C, Kabul, basic, something. And we can see that the variable more products is filled only in one part of cycle, not here. So if we don't go to that path, so if the product qualifier is not presented, the more products variable will not be filled. And there is some chance that due to garbage stack, it will be equals to 3 comma. It's like low possibility, but still. But for some reason, LLVM optimizer thinks that he's smarter than us. And he thinks that initially this variable equals CLI comma. And because of that, all the cycle became endless. If you look at the disassembly, you will see that there is no any filling, and there is no initial check for containment of comma. The cycle is just endless. So the fix will be just to initialize variable, for example, with 0. So it's the problem with variable being not initialized. Any questions? It's quite a short presentation. Okay, I'm nearly finished. So the most common problems we face during moving from i10 to x86 are these three ones: variables too small, variables too big, and variable is not initialized. It was in different products, in layer products, in compiler itself. It works, but when moving up to x86, it stopped working. So that's all for me today. Any questions?
With this issue,
It's about the native OS build, so it's not public yet. We're still testing the native OS, and all the layer products. We of course test them before releasing. Yeah, so I believe we will clean all of this before the native OS release.
The problem I asked about is a third-party code.
Yeah.
Worked on one system, one customer system, but they was having some problem that I wanted to try and investigate.
Mm-hmm.
Tried it on my system, it didn't work for me.
Yeah, it's there.
And it was variable too small.
Yeah.
But on his system, it worked. Okay. The
Yeah.
only idea I can come up with is it's a different underlying piece of hardware, and out of order execution could have allowed it to work.
I don't know. Maybe for sometimes when I get the report about the problem that is occurred, I try it on my system and it works fine.
That's right.
Yeah.
That could be.
Yeah.
You've got a different underlying chip.
Yeah. Maybe some other software, maybe something running. I don't know.
That's typical. When it doesn't work on the customer's side, it always works on your machine. That's typical.
It can also be underlying memory layout based on any number of parameters. So there's, chip is unlikely, right? But memory layout is more likely. Yeah, no, I mean, this is, again, Vadim was the only one. We had problems with this even before we had cross compilers. We found some things where the memory allocation algorithms on two previous architectures, which preferred to have things on aligned boundaries.
Yeah.
And so therefore it's packed the variables, and the LLVM compiler is perfectly happy to put a byte next to a long word, next to an array, right next to a word, and run over is a much bigger problem.
Yeah. Maybe also a difference between the hypervisors. Maybe on VMware it works, on KVM doesn't work. Yeah.
So I had one issue. So we had virtualized the VAX to run on emulation. They've been running this program for 30 years without an error, without an issue.
Yeah.
Interfacing with a analog device via serial connection.
Mm-hmm.
And it worked for the last 30 years. Everything about the application worked in the new environment, except they kept getting this bogus data that they didn't know what it was. And it turned out the data was always being sent, but the machine was too slow and missed it. So I didn't know there was extra conversation happening. So I'm surprised we haven't run into that timing issue where, VMS never missed it. Well, didn't know about it because he never got it. His cycle never came around fast enough.
Yeah.
Say, oh yeah, I have more data. No, it was a timing issue. So that's the other one potentially
Yeah.
you can run into.
Any more questions?
The trends of IGK were available as variables.
Mhm.
It's automatically entered. That considered. included? Could we share some?
It's unfortunate.
Yeah, it's maybe.
Yeah.
Yeah.
So, well, it is.
Yeah, so most problems is due to some garbage in the stack that came to your variable. Yeah.
One problem, two,
Yes.
another doesn't.
Yeah. We thought maybe do some workaround like pushing RBX twice and then restore it twice, just to make sure that there is some alignment. But we'll just hide the problems further, and maybe on some port to another possible architecture, it will be exposed again. Yeah, so it's all for me.
Clean the variable into zero memory in advance to see what's going to happen.
Yeah, you can do that, but it's maybe some performance.
Time consuming, yeah, I know.
Yeah.
But that's like investigation, say.
Yeah, we have some internal options to zero initialize all the local variables. So sometimes we can run the programs non-optimized. We can zero initialize memory. We can zero initialize memory and then optimize some. Yeah, it's the easiest way to find that it's one of these problems to zero initialize in the beginning. Yeah. Yeah. So thank you for listening.
Thank you.